Okay, good morning, everybody. Welcome to Oracle Code 1. My name is Ben Hale. I am the lead of the Cloud Foundry Java experience, which this isn't the audience that I normally talk to. So to give you a little background, Cloud Foundry is an open source PaaS, platform as a service, biggest one used in the enterprise these days. And I run anything having to do with Java applications running on it. My background is about 12 years ago, maybe 13 years ago now, I was the first person hired at Interface 21, which became Spring Source. And so I've also been a core committer on Spring projects for that entire time as well. And with me is Stephane Maldini.
Hey, so I'm Stephane Maldini. I'm the lead of the project Reactor. If you haven't heard about it, it's a reactive foundation for Java 8, and that's what Spring 5 and Spring Boot 2 are using for the reactive features they offer. So I work for the Spring team as well at Pivotal, and I've been doing reactive stuff for a long time now. And I guess today is going to be a bit more forward-looking. What's the next step for us in the reactive space at Pivotal? And so we're going to just talk about that with that.
Great. So we're going to be talking a lot about reactive programming here. So to get started, how many people today are writing reactive programs? Doesn't matter really even what language. OK. So let's call it about a third of you. How many people want to be writing reactive programs? Is that a little bit bigger number? Great. OK. So reactive programming is the next frontier for Java if you need to do high efficiency computing. And this is a big deal. When we talk about reactive programming, there's not necessarily an obvious performance benefit to something like this, but there is sort of an effective performance benefit in the fact that a given application written reactively rather than imperatively generally is more efficient, which means you can have higher throughput with fewer resources to be using it. So fundamentally, when we're talking about reactive programming, we're talking about a non-blocking programming model. That's sort of the key bit of this. And it is often paired with asynchronous behaviors. But the key thing to remember is when we talk about reactive programming, we don't actually have any strong opinion on whether or not behaviors should be asynchronous. So if you took a look at Project Reactor or RxJava or something like that, one of these reactive frameworks, the most efficient thing that it can possibly do is sort of run things completely synchronously on a single thread where it can do it. Typically, we end up to a place where we need to do some sort of blocking, waiting for a network request, going to a database, something like that, and then we'll behave in an asynchronous manner only at that point. But all the programming, all the execution up to the point of blocking has been done synchronously. Now, obviously, I talk about it being fundamentally non-blocking. We often pair with asynchronous behaviors. But one of the key differentiators from asynchronous programming and reactive programming is this idea of pull-push backpressure. Anytime you're dealing with two parties communicating with one another, and you can imagine something like two microservices communicating with one another, there's always a problem, right? There's always a risk if the client side of that connection makes a request to the server side and either accidentally or intentionally requests too much data, right? You go to a database and you accidentally request 10 million rows for some reason. What ends up happening there is you shift either two bad outcomes happen at that point. You either, one, shift a whole lot of data to the client, and the client's heap explodes because you have just requested way too much data. You go completely out of memory. Or a bunch of data is generated on the server, filling up sort of the TCP buffers, trying to transfer that data. And now the server has a problem where it has filled up all of its heap and it can't get all of its data out. So reactive programming, when we talk about it, especially in the Java world, but generally when you talk about sort of the Reactive Streams specification, has this idea that a server cannot send a client, right? So a publisher cannot send a subscriber a piece of data until that subscriber has requested it. Says, hey, I need 8 things, or I need 16 things. And then that server has the ability to send 1, 2, 8, 16, as many as it needs to. But once it has sent everything that it has, it will no longer be able to send any more data until the client is ready for some more. And so we've been really successful with reactive programming. 3 years ago, we Project Reactor came on the scene. We started talking about it at something like Spring 1. We said, hey, reactive is a thing that you should be worried about. And then 2 years ago, and then 2 years ago now, I guess, we then came on and said, hey, Spring's going to support this kind of programming model, right? And so Spring comes and it has something like this, something that we call web flux. And so this code, if you guys are familiar with sort of Spring-style syntaxes for running applications, we've got a method. This is going to listen on /health for something. And this particular thing is going to use something called the web client. Doesn't really matter what this API is. It's like REST template or something like that, to asynchronously and non-blockingly, so in a reactive way, go to my alpha service and get its health, go to my Bravo service, get its health, and then map those two things, right? Map them into a composite health item that will then be returned. But the key thing about this is that this happens all in a reactive way. It's completely non-blocking. It happens asynchronously. And so while it will obviously take some period of time to go to the alpha service and the Bravo service and get their data, we don't occupy a thread. We don't occupy any extra memory on the thread stacks and things like that. We can do this as efficiently as possible and then return data back out. So we've got a good programming model as of a couple years ago for doing web applications. But there are still some barriers to using reactive everywhere. There are certain, call us zealots perhaps, that believe that reactive programming really is the future. You don't have to believe that. What we see is that for reactive programming, there are certain places where it is a really, really obvious programming model to adopt. A place like anytime you're trying to do coordination between multiple microservices. This is a really obvious thing because today we have huge problems. You're running Tomcat, you have 200 threads. All of them are trying, you sort of have occupied those threads making some sort of outbound calls to other microservices. And now all of a sudden you've got a service that's got 1% or 5% CPU usage, and yet no more connections can be served. So reactive programming is a real obvious win here because now all of a sudden if we give up those threads while we're waiting for microservices to respond, we can do some more things, right? We can handle more tens of thousands of simultaneous connections potentially. But if we take a look at some of those barriers, one of the first big ones is data access. So right now, if you want to access a data store in some sort of asynchronous way, we have MongoDB, Apache Cassandra, Redis, sort of the NoSQL databases. We don't yet have reactive databases, although there is this R2DBC project that is also one of my projects that is aiming to rectify that, so if you're interested. But also, we don't really have a good answer for cross-process backpressure, right? So if we remember this demo right here, or this example right here, this does actually have reactive behaviors. It does have pull-push backpressure, but only to the edge of our process. There's no way if this thing needed to return like 100 gigs of data to me, right, this call out to /health, there's no way for me to slow down the producer of that, the publisher of that, so that I don't explode and it doesn't explode. So we're here to talk today about RSocket. RSocket is a network protocol that aims to bring reactive programming constructs to the network.
So with RSocket, we really place ourselves at the same level as HTTP. So when we talk about a protocol, it's really a layer 7 protocol here. And I'm going to go into more details about it. What RSocket is offering goes beyond HTTP. It goes to the extent of 4 interaction models. We have a request, void, or Fireandforget. With a protocol, with RSocket protocol, you can send a message to a remote server or remote receiver, and you don't have to expect a response. So Fireandforget. It's pretty efficient to do like ping or logging or non-critical data transfer. Then you have request reply. And request reply is exactly what you have with HTTP. You send a request and you can expect a reply with any data you want on both sides. You have something different then, which is what we call request stream. And request stream is actually sending a request to a server, like a request in HTTP, but not only receiving one response, but multiple responses. So think about subscription, for instance. You are one of the prominent RSocket user, Facebook. You are RSocket. You are a Facebook device. A Facebook client application. You subscribe to new feed, new news, basically, and you receive multiple news over a single request. So you subscribe to many responses in that case. And then you have an ultimate interaction model, a bit more complex, but really interactive. It's sending a stream of requests and receiving a stream of response. So you can send multiple requests and receive multiple responses, and it can be useful for really interactive scenarios like Siri, for instance. Siri will interact with a server with many requests, many questions you have, and we'll expect multiple response over the same connection, over the same stream, multiple response from the server. So we'll add more and more context or more precision to the Siri response over time. So it's 4 interaction models. And one of the great things we have in RSocket as well is the multiplexing feature as well. So what means multiplexing? It simply means for each message we send, we associate a stream ID, so we can reuse the same connection, very much like HTTP2. That's normally nowadays a kind of a well-known pattern, so we avoid opening a new connection for every single message we want to send. So you can say HTTP 1.1 has solved kind of solves the problem with HTTP pipelining, but it doesn't really achieve parallelism because when you use HTTP pipelining, you have to wait for the response to send the next request, and then on the same connection, you wait for the next response, etc. With multiplexing, you can interleave any request and response, so you reuse the connection with many parallel streams, and that's more efficient. You don't have to wait for the response to get back. So it's pretty much like TCP in some sort, in fact, because TCP was not prescribing the use of the protocol, the transport to be sequential as HTTP. TCP was just saying, okay, you can send messages. I'm actually accepting that much messages. That's what we call the TCP flow control at the byte level. And that's pretty much it. It doesn't prescribe you to send different messages over the same connection. So it's normally as small as TCP. The other thing we like in RSocket is because it's a layer 7 protocol, it's what we call a framing protocol. It doesn't say you have to use certain transport to work. You don't have to use TCP to work. You can even use UDP if you want to. You can even use WebSocket, something very high level, because what you do with RSocket is just framing the data you're going to send with extra information. It's a byte delimited, length delimited frame. And that's pretty much it. If you have a receiver driver and a sending driver that understands how to encode and decode this information, that's all you need. You don't need to have UDP, TCP, for instance, to work. You can use UDP. And there is already an implementation called Aaron. And that's a pretty fast and efficient implementation of UDP as well. So that's another interesting thing. It's transport and agnostic. And the other thing we actually like in RSocket is it doesn't create an arbitrary client-server interaction. You don't have to be a client and you don't have to be a server to say, okay, I'm going to only ever serve request. I'm an HTTP server. I'm going to serve response. I'm going to do that only in my entire lifecycle life. And you don't have to do that. In TCP, we don't have such very constrained roles where someone is a client and someone is a server. Obviously, someone has to open a port and someone has to connect to a port. But you can be actually bidirectional. Someone, once you connected, can actually act as a server and serving response to a remote endpoint you are connected to. And we already have other protocols doing that nowadays. And even if you think about messaging transport such as Kafka or RabbitMQ, for instance, they already kind of do that. They react to, regardless of them being client or server, they react to incoming traffic. And that's another interesting thing we have with RSocket. We used really the fact that we can be bidirectional, and that's an important feature, and we'll see why also it's an important feature as well. So the extra thing we have in RSocket, because so far it compares to a few other protocols, is the backpressure principle. It's embedded in RSocket. So RSocket just means, in fact, reactive socket, and it has been heavily inspired by the specification Reactive Streams. And we have really mapped all the framing from the interactions you find in Reactive Streams. So we will find on next, on complete, on error frames, type of frames. But also we will find the request and cancellation type of frame as well. And the request really means you can send, as a server or as a receiver, you can send to a sender, I'm ready to accept 2 messages. It doesn't act at the byte level, it acts as a score. So you send to a sender how many POJO you are ready to accept. And once the sender receives this information, and only then, it will be able to generate this data. So before then, no data has been generated unless you do some prefetching technique, and that's something you can obviously do on the client side or server side. And only then you send this data to the server or the receiver, and that's it. And you can iterate on that, and that's the protocol in action. The server will never be overflown by data it doesn't actually ask for. Otherwise, it's a protocol violation, and the connection will be rejected altogether. So that's pretty important to make sure that you have boundaries around your application, and you can guarantee a super high availability for your application, because you know exactly how many data are going to flow through your application at any given time. And so once we next step into the stage of all of these features, we go even further with RSocket with something we call resumption. So every receiver or sender in RSocket can track the message, the last message that has been sent with an index, for instance. So it starts with 0 in that case, and we want to send the 1 and 2 messages, obviously after having received the demand for these messages, but here we only focus on what messages have been sent or are going to be sent. And once we receive these messages, the server or the receiver track the index and say, okay, I have received 2 exactly. And I am now ready to receive the next message. It doesn't reply exactly where it is because it's all asynchronous. You don't have to wait for the server saying, okay, I have received 2 messages. All we know is each side, without knowing each other, have sent and received 2 messages. So what happens then is, if you have a problem, if the connection breaks, and that's another interesting feature. For instance, again, I'm using Facebook as an example, but they have this problem, this pretty big problem when you as a user use the Facebook application, and you move between cell towers or Wi-Fi connections, and you drop your connection. So in that case, the data you are about to send or about to receive is going to be dropped as well, or you don't know, and that's a problem with distributed system. You don't exactly know if the data has been received or sent. And another problem that RSocket is trying to solve for you as a protocol is exactly this one. We know, because each side has tracked exactly what has been sent, we know when we try to resubscribe or reconnect to the receiver, we know where we can start from. So in that case, we drop the connection, and then we will have to reestablish the connection, and that's where this feature is used, the resumption feature. So because we dropped the connection, we have received from the receiver exactly what information the receiver has seen for the last time. And in that case, it was the number 2 message. And so as a client, you know you have already sent the message number 3. But because the server told you only he has seen the message number 2, you have to restart from number 2. And that's at least once guaranteed delivery, because you will maybe send again the same message, but you have to do it because the server hasn't seen the message number 3. So we're sending again number 3, and that's great because now the server has actually received it, and on his side continue to track where it is. It's pretty huge, and obviously, it requires you to have some state, so you need to keep track of which message you have received or which number of message you have received. But the driver takes care of that for you because it's a feature embedded in RSocket. Some drivers already do it, like the C++ implementation, and we're going to see there are multiple implementations of RSocket, but the Java driver is a work in progress. So if we take a step back, another interesting thing about RSocket is since it's a protocol, it can work on any language. It can work on the current implementation, for instance. So we have a JavaScript implementation. We work on the browser, for instance. We also work on C++. That's mostly what is used by Facebook, in fact. And the JavaScript one is something you can use also as a browser because it doesn't only work on Node.js, for instance, here. You can use it as really a rich UI driver to communicate with your backend application. And it works on Java as well. The interesting thing is, since we work with many different transport, we can compose this protocol. One client can be connected to your backend with TCP or WebSocket, for instance, and one backend can be connected with TCP and directly TCP, and another connected with UDP. So without losing semantics, you can compose these services with RSocket because the backpressure is going to be propagated end-to-end. And that's really the nice thing about this. At the very edge of your API, you will be able to have a lot of incoming connection, asking a lot of data from your backend databases, maybe 3 nested levels below you as microservices calls. And up to these database calls, you will be able to receive the information of how many things you have to pull from the database, control how many data you have to pull back, and send to the sender, to the requester initially. So you have this end-to-end nice propagation, which comes for free with RSocket. So it's not only about this stuff, but we cover a lot of things with RSocket right now. We have Java, JavaScript implementation, C++. We have also a dedicated Kotlin one with the support for coroutines, GraphQL implementation with Flow, and we have multiple styles. Ben is going to talk about this as well. And another interesting thing is it doesn't prescribe how you encode your data. So we can use today things like protobuf or Thrift, Apache Thrift. But you can also do JSON and your own custom encoding or decoding facility. It's really binary protocol, so you can decide whatever you want to use to encode your data. And that works, again, on top of many protocols. Right now, we're working on HTTP 2 implementation because we can use also HTTP 2 streams. But if you already have WebSocket support in most of your infrastructures already today, so you can use WebSocket and TCP and run UDP as well. So all of that is pretty theoretic. How does it look like for real, Ben?
Yeah. So clearly, the flexibility that you see in this chart right here is one of the huge selling points for a protocol like this. The fact that it is language agnostic, that it is sort of programming style agnostic, that it's payload agnostic, that it's transport agnostic. We have, a lot of choice here while still getting the benefits that you see from the RSocket protocol, just sort of the blue layer in there. But for this, we're going to talk about the Java API. So the Java API is fundamentally these 4 methods. We said there were 4 interaction models at the very beginning: request, response, Fireandforget, request stream, request channel. One of the key things, my friend Stephane here is really happy. You'll notice that the types there are actually Reactor types. So the RSocket team was one of the first adopters of Project Reactor. They've been really, really happy with it as they've gone along. So if we take a look at that first one, that request-response interaction, this is exactly request response as you understand it, right? So standard HTTP style, send one request, get one response back for it. And it's still likely to represent the majority of all the requests for the foreseeable future. There's a reason it became popular enough to make HTTP and to be evolved into HTTP 2. This idea of I make a request and get a response is really, really key. But one of the things that you might not realize is even something as obvious as can surpass what HTTP does today because it is both asynchronous and multiplexed. So we can be more efficient. We can get more data transferred in a more efficient way across a single connection than you might otherwise with existing protocols that are out there. So an example of something like this is I have my banking app on my phone. I go and request with my account number, and it's just going to give me a response back that's the balance of my current account. The next is sort of a specialization, an optimization of this. And Stephane mentioned a little bit earlier, this idea of a fire and forget request. And a lot of people don't sort of see the idea of when would I want to use this? Why is this any better than just a request with a response that it's a no-op? And it turns out that you can actually get significant performance improvements simply by assuming that I can send a piece of data and just be done with it. I don't have to listen for the network to come back and acknowledge that it received. And in client-server style processing, it means that the client can immediately release any resources that it was holding when it went off and sent that message in the first place. So one of the great examples of this, and it's sort of because HTTP is structured the way it is and so many people use HTTP, you don't really think about the idea, what if you could tell a client device from the server that I want you to start sending me back event logging, right? Like you have someone on the support line, you're trying to do some sort of diagnosis about exactly what's going on an app on the other side. And it might be, a cell phone app that's sort of line of business inside your company, or it could be someone else on another server at the end of a sort of server to server inside the data center connection. And you could literally say, okay, you, client foo over here, this one particular connection at the other end, I want you to start streaming me your log data so that I understand what is going on. When I send you data, I want you to start telling me exactly what you see over on the other end, making sure that everything's working. And you can do that on a very fine-grained kind of thing. And this is the key, is the fact that the other side of that connection is sending you a bunch of data, if a line gets lost here or there, who cares, right? It's not critical. Right? It's not mission critical. We just need to collect a bunch of data over the course of a day, and if lines here or there are lost, if log statements here or there are lost, it's not that big of a problem. So fire and forget ends up turning out to be a really, really good diagnostic tool. We have the request stream interaction model. So it's analogous, as we said, to the request response that we saw a little bit earlier. But in this side, what we're going to do is stream back the collection of data. So rather than you going and getting me all of the persons, right, like I want you to go query for something and you give me all of those in one go, it basically just sends back a stream. Think of it like an event stream, but with data in it instead. It's going to start handing back whatever these payloads are. But one of the key things here is the request end semantics we talked about that make up reactive programming, this idea of pull-push backpressure, because this actually makes things really a whole lot easier on the producer of that data. Imagine the producer of that data is a database of some kind, right? And I want you to return me all of the customers for my entire bank, or in this example that you have here, all of the transactions in my entire account since the beginning of time, right? If the database has to sort of swell all that, has to materialize all of that data, even if you start, you take it as fast as you can, but it can't send all that data across a network connection, there's a period of time where a lot of data has been materialized on the server that's occupying resources that it can't get off. So in this case, we use request end semantics to say, okay, I just need the next 10 rows, right? I need the next 10 transactions, or I need the next 64 transactions. And that is a signal back to the producing side of this connection that it should only materialize the next 64 and send it over. It doesn't have to materialize the whole system, right? It doesn't have to materialize that entire data set. All it needs is what the client can currently handle. And that means if the client, sort of switches off to another page or finds some piece of data that means it can cancel, it means you've not materialized a bunch of data that you needed to. And that ends up being really, really helpful when it comes to sort of large data sets being moved back and forth between two systems. The final interaction model that we described was this request channel interaction model, and this is sort of the most generic. You can implement all of the other interaction models sort of as a specialization of this. This effectively means you've got a pipe, and anybody can send messages back and forth as long as you are subject to the request and semantics. So we often see this used to request a burst of initial state, and then you listen for subsequent updates. So this is how Facebook uses it, for example. In our banking scenario that we saw before, maybe I want to send you my account number, and you're going to give me a real-time stream of account transactions, right? So what we're going to do is we're going to say, okay, I'm now looking at a page of my transactions. Hand me all of that data, right? Now you're going to start streaming my data as I sort of scroll through, and as new sort of new bits of this never-ending stream come up, we go and request more data. But at the same time, what we could do is then like place a filter from the client side. And so there's now a message that goes back across the channel and says, okay, a new filter has been applied to this query. So now as I start going, I want to get a smaller subset of the data that I had seen before. And this allows you to effectively say, I don't need to open new connections. I don't even need to start new streams. I just have a big pipe that we can just pass messages across, but with all of those sort of reactive semantics that we saw before. So what does code like this look like? All right, so in this particular case, we're going to take a look at what we call the raw client. So if you took the interface that I showed a little bit earlier, this is how you use it. You have this RSocket factory, you connect it. Notice we specify a particular transport here. In this case, it's going to be TCP. If you wanted to and you wanted to use WebSockets, you'd have a WebSocket transport create, sort of where the WebSocket connection is. Or if you wanted to use HTTP2, you could say HTTP2 transport or UDP or something like that. So it's really like sort of baked into the entire usage of the API is the idea that RSocket sits above the transport. You need to specify what you want to use, but it is completely abstracted away. Nice API for just picking something. So once you have that particular client, you're going to execute request response. We're going to put in some default payload. Who knows what that default payload is going to be? It's just a byte buffer, just a bag of bytes. So maybe you serialize JSON down. Maybe you serialize a protobuf definition into it as well. And data is sent. Data is received. Request response, so we get one back. When that is complete, so we sort of get a notification as part of reactive programming, we print out something. And so this just goes. Now, it's pretty easy for you to say that this is too low level, right? Like we're managing sort of request response, we're managing this default payload, we are responsible for doing the serialization of whatever our types are back into these byte buffs themselves. So one of the key things to remember is RSocket's flexibility means that it was designed to build other things on top of it. It is certainly possible, right, to it's a serviceable programming model to use the RSocket interface directly, but we want probably something a little bit nicer. And when we talk about making things simpler, there are a couple of options already out there today. So there's an RPC style, so protobuf code definition, think gRPC kind of programming model, as well as a new messaging style from the Spring team. So if we take a look at that RPC ContractDriven Style, you can imagine a record service here, and we define a protobuf definition that this has, records request returns a stream of those particular records. That means then we can generate code from this. And the code we generate looks a lot more sort of idiomatic. It matches our internal programming model and under the hood translates onto those RSocket frames and that RSocket API, but doesn't require you to know it, right? So now we have one of these record service clients and it knows how to say, okay, I want you to go get me the next 16 records from whatever this is. It goes out there, we subscribe to it, and as those come in, we sort of, we print them out, or we do whatever it is that we need to do. And underneath the hood, it's translating onto the RSocket API that we saw a little bit earlier, but it's also then taking advantage of the RSocket protocol. Behind the scenes, it's doing request end semantics. Resumability is in place in a way that's transparent to the programmer at this particular level. All right, you still kind of need to manage some stuff like how exactly the RSocket client, so from the previous slide, how we created the RSocket factory client, how that gets plugged in. But all in all, what we have is a wrapper that is sort of semantically consistent with the rest of your application. But as we said, one of the main reasons for using an RPC style, for using this contract style development is it means that you can use the same definition that we saw before, but build it into another language, right? You could build it into JavaScript. We can use the same protobuf compiler kind of thing that can build a record service client, set the max results, and subscribe for those same things to come in. And now all of a sudden you have interop between all of these different languages using a consistent RPC style API. Okay. Now, I am personally not a super fan of RPC style APIs, opinion. You may or may not share with me. I just remember the last time, I'm old enough to remember the last time we tried RPC and it didn't really work for us. So there are alternatives, right? If you're more of a loose coupling messaging style person, I apologize for how small this font is on here. But effectively, if you're familiar with the way Spring does messaging or Spring does web endpoints, things like that, you'll recognize what this is, right? Now we've got a class that has a method on it, takes in a payload, returns a mono of that payload. And we have a message mapping basically saying that if a message comes into me across one of these connections and it wants to go to /canonical, this method gets invoked. We return this Project Reactor payload back, right? We basically wait 10 milliseconds and then create a response from it. And that gets handed back and is handled sort of in Spring as a framework. Same thing on the lower one. If somebody comes in /async, right? In this particular case, what's happening is we take the payload, we map the input to that payload to some sort of asynchronous behavior. We make another call back out to another database. And what we end up with is this real loose coupling between the client who made an invocation into it. Maybe we need to make a forward invocation back to something in our somewhere else in our data center. And all of this still ends up, because we're using RSocket the whole way through, with Reactive Streams over on our JavaScript client, with its request end semantics internally, request end semantics over RSocket that gets us to this particular application in Spring. It then gets to manage those same request end semantics back out throughout its entire data center and its microservice mesh. And so that's sort of the promise of this whole thing, is this protocol sort of encapsulates a bunch of best practices we know about programming distributed systems, but then allows you to decide what style of programming you want on top. If you want contract-driven RPC style, you can just layer that on top of the protocol. It was designed so that you could do that layering. If you're the kind of person who likes a looser coupling using a messaging style with routes on it, we can do that as well. So all of these are available to you when you're using RSocket. And so while we think that that's really good, RSocket goes even further beyond that. Effectively, what happened was the team at Netflix who did all of the original Netflix OSS stuff, so things like the circuit breakers and Hystrix and things like that, sort of looked back and said, what if we could bake all of this into a protocol? What if a lot of the things that we saw that people were writing a ton and ton of code about, we could bake more than just reactive streams into this protocol? And so there are a couple other features I want to notably highlight. Obviously, we talked a little bit earlier about resumability, right? This idea that given a broken connection, both the requester and responder, the client and the server, actually sort of have a coordination and can guarantee that you can bring things back up from the dead. But also, we have metadata and data in each and every frame. So a frame that is sent over, you might think, oh, this just has a JSON payload in it, or it just has a protobuf payload in it, but it also has metadata attached to each one of those frames. And so now we end up with something that's super flexible. It effectively means that every single frame that we send across one of these connections could be sort of a standalone thing and contain enough information that the receiver of that particular frame knows how to decode it or knows that it wants to ignore it because it doesn't really care. Right? It means that in that example, when you're using a channel, maybe sometimes you're sending images and sometimes you're sending video. And so the MIME type associated with the payloads in each one of those ends up being different. The protocol also supports fragmentation. So payload frames themselves have no real upper bound when it comes to the size. I guess it's probably the size of an array, so like int.max in Java kind of thing. Languages, I think, are much more likely to impose size restrictions than the protocol itself is. And it is very well suited to sending these kinds of payloads. So Facebook obviously used it. They send everything from little text blurbs, right, in your newsfeed to images, these days video as well, realistically. Netflix used it for a long time, sending video as part of these payloads. But one of the key things to remember, especially if you're going over sort of the open internet or you're going to devices that have slow or intermittent connections, you probably don't want to send all of this episode of Stranger Things in one payload, even though you technically probably could. So they sort of thought about this and said, what we actually need to do? We need to have fragmentation as a first-class part of the protocol. This means that after all of sort of the request end semantics have been satisfied, that I am requesting 8 whatevers, we'll then take those 8 whatevers, and for each one of them, we'll attempt to subdivide them. We'll break them into something significantly smaller, but we'll do it in a transparent way so that when it gets over to the other side, it can be be reassembled transparently again and handed to the client that asked for it. And the real reason this sort of transparent fragmentation is really important is this idea of how request end works. We said that TCP wasn't great, even though there is buffering and you can only get a certain amount of, a certain number of TCP data to you before you have to ACK it back and they'll send some more. So there is a bit of flow control at that level, but programmers can't reason about the number of bytes that need to be sent to constitute my POJO, whatever it is. First off, we don't know how it's going to be serialized, things like that. So working down at that level, at the number of bytes and doing flow control there is difficult for us to reason about. Now we're up at request end, we can say, okay, I want the next 8 rows, the next 8 POJOs. That's something I can reason about, and roughly how big that's going to be in memory for me, how much data that's going to be for transporting. If now all of a sudden somebody starts fragmenting these, and I ask for 8, and that gets me 1 1/3 of my payloads or something like that, or a variable number of my payloads of these POJOs that I can reason about, we have the exact same problem. So request end semantics sit sort of transparently around you asking for the next set of items. Next feature is this idea of cancellation. And a lot of people don't really sort of strike on why cancellation is important initially, but eventually come to love it. This idea that any interaction I do, when I do a request and I'm waiting for a response, I do a request, I'm waiting for a stream of responses, I do a channel request so that we just have a live thing open. At any given point, either end of it can send a cancellation frame and basically say, I'm done. Whatever you were doing over on the other side, you can go ahead and abort that. And this ends up being really, really powerful. So obviously, you know why you want to do it for a request stream and channel, right? Like if the stream is attempting to send you, 10 million rows or something like that, being able to say, okay, I got the 500th row and it had what I needed. We'll just go ahead and cancel this. Don't bother materializing anything new. Don't load anything up into memory. But we also can use it on request response. And so the Facebook team is really, really big on this in the sense that they have a lot of payloads. If you sort of have any inkling of what the inside of Facebook must look like. It can be very expensive to generate a bunch of stuff, right? It can be very expensive for you to go back to 14 different microservices internally, get them all to coordinate, wait around for their responses to get to you before it can even be responded. So the idea that you can cancel even a request response before data has been completely materialized ends up being really valuable. And then the final feature as part of the protocol that I want to talk about, and to be clear, this is certainly not exhaustive. There are a ton of different features that are in here beyond these, is this idea of leasing. So reactive backpressure guarantees that a producer can never overwhelm a consumer. It cannot send more data than the consumer has requested, but it doesn't actually stop a consumer from overwhelming a producer, right? You could imagine a really chatty client, or say hundreds of millions of really chatty clients, trying to go to a single server and say, hey, send me data, send me data, send me data, send me data, and now all of a sudden this thing explodes. So leasing as part of the protocol effectively allows a server, sort of the producer side of this equation, to tell a client, here are the number of requests you are allowed to send me in the next period of time. So you might imagine a server that watches its CPU usage. And as long as it's not, sort of not over 80% CPU usage, everybody can request as much as they want. But as soon as it starts creeping over 80% CPU usage, it starts saying, okay, all of you clients, you get to submit me 10 requests in the next minute, or call it 100 requests in the next 5 minutes, or something like that, and until things sort of come back down to an equilibrium. And you can use sort of exponential backoffs and algorithms that you choose to sort of tell clients that contractually they can no longer ask you for information, but that's okay, right? Sort of the goal is stability in this particular case, not throughput, because what's worse than going slightly slower than you might otherwise do? An entire server falling over because it's been loaded up too much. We want to bake that into the protocol itself. And this is used generally for client-side load balancing. Clients have a bunch of different servers that it might be allowed to connect to, especially in a data center sort of scenario. And so they all go, so, okay, you've told me that I'm no longer allowed to make a request to you. I can't open a new stream against this server. Let me go to the next one on my list and start going to them. And that second connection to the second server has different leasing semantics than the first one does. This one I'm still allowed to go to unlimited requests over an unlimited period of time. So we have a way to sort of facilitate client-side load balancing without preventing server-side load balancing as well. We generally see with RSocket systems, both client and server load balancing happen simultaneously with one another. So that's the final feature that we're going to talk about here. We got just a minute or two left to go. So RSocket, as we said, a bidirectional multiplexed message-based binary protocol. So definitely a huge mouthful, but it is sort of what you would be looking for in protocols if you were designing a new protocol today. Uses Reactive Streams backpressure, that pull-push backpressure that we saw, and it provides those 4 common interaction models. We value its flexibility in transport, payload, language, programming model, especially around programming model. We're always interested to hear people who start using and experimenting with RSocket, finding out what it is they like, where we should focus more effort in improving it. And there are, as we said, a myriad other features to make it great for modern application-to-application communication. So from Stephane and I, thank you all for listening to us today, and happy to answer any questions. Oh, a question at a microphone. Hey.
Netflix, and they've been building a lot of stuff in kind of an old implementation of this direct data structures. And we're moving more and more to gRPC.
Correct.
Instead of.
Yep.
Can you talk a little bit about your thoughts about gRPC versus?
Yeah, Stephane, do you want to take that, or shall I?
Yeah, so the question is what, let me rephrase it the best way I can. What's the differentiator between gRPC and RSocket? That was the question. Okay. So one major difference is gRPC is based on HTTP2. So that's one limitation. We want to have something more flexible with RSocket that works on top of anything. For instance, on Foundry right now, currently, we support a WebSocket connection, but we don't support HTTP2. It's coming with our next generation of PaaS and Kubernetes-based environment. But right now, if you want to use a kind of messaging protocol or RPC-based protocol like that, you cannot use gRPC because we only support WebSocket connections for the clients. So that's a major difference. Until very recently, I've seen some example of how you do that. It was really heavily based on protobuf, but you can change the encoding and decoding nowadays strategy for gRPC. But at first, it was very flexible for us to see that RSocket can have different encoding and decoding facilities. For instance, Facebook doesn't use protobuf. They use Apache Thrift or the own version of Apache Thrift. So it's pretty important to have this flexibility. It's not nowadays that much a differentiator, but everyone used gRPC for that reason.
Yeah, I think the other thing to keep in mind when you're talking about gRPC is that it is still fundamentally based on a flow control that's at the wrong conceptual level for developers. Underneath the hood, you still have that situation where a server can generate too much data and either blow up the client as it tries to send the data over, or the server that it's being generated on, depending on how you're using HTTP2. So there are limitations in the HTTP2 protocol itself that make RSocket a better choice. And that's not to say gRPC can't be updated in such ways that it could bake a lot of that framing into it, but that's not where it is today. Yeah. Okay, so our time's up. To respect the next group of people, we'll move outside into the hallway and answer more questions.